So, next we will be looking into arithmetic circuits. So, the circuits there are many digital circuits that perform arithmetic operation like addition, subtraction, multiplication, division, etcetera, and they by themselves form one special class of circuits. Okay. So, these arithmetic circuits are looking into that. So, the first example of this arithmetic circuit that we will consider is that of an adder. Okay, this is an example of iterative design. So, iterative design means you have got a basic block and that basic block is repeatedly used for getting the more complex designs. Okay. So, that way this adder is an example of this iterative design. So, we design a 2-bit adder and using that 2-bit adder, so we can expand it to 3-bit, 4-bit, 5-bit like that. So, we design an 1-bit adder circuit and then expand to n-bit adder circuit. So, this 1-bit adder, so it has got two 1-bit inputs and it produces the sum of them, sum and carry bit, and accordingly and then this 1-bit adder can be expanded to have any arbitrary n-bit adder. So, we will look into half adder first. So, which is a 2-bit adder and inputs are bits to be added and the outputs are result and possible carry. So, when you are adding two 1-bit numbers, say so if the bits are say 1 and 1, then the sum is 0 and there is a carry of 1. So, this has to be generated, whereas if it is 1 and 0, then the sum is 1 and the carry there is no carry. So, carry is 0. So, we can have this type of situation or say 0 0, sum is 0 and the carry is also 0. So, this way we have got half adder. So, this is a 2-bit adder and then output and this the sum and carry. So, these are the two outputs. So, on the other hand we have got full adder which includes a carry in also. So, it has got these 2 bits to be added and it has got a carry input. So, that is this actually all these 3 bits will be added to produce the sum and the carry. So, the half adder is something like this. So, this is the logic diagram of half adder. So, this is the so truth table is like this. So, as I have said that it has got inputs x and y and it has got two outputs sum and carry. So, how this if 0 and 0 are added, these two bits are added, then sum equal to 0 and carry is also equal to 0. If it is 0 and 1, sum is equal to 1 and carry is equal to 0. 1 0, sum equal to 1, carry equal to 0. 1 1, sum equal to 0 and carry is equal to 1. So, if I look into the corresponding circuit, then this this sum output, it is nothing but the XOR function. You see, whenever x is 1 or y is 1, then only the output is 1 and that is in the exclusive OR fashion. So, this S output is the XOR of x and y and the carry output is the AND of x and y. So, C is equal to 1 when x and y both the inputs are at 1. So, we have got the logic diagram of half adder consisting of one XOR gate and one AND gate. So, S equal to x XOR y and C equal to x y. The other and full adder. So, in case of full adder we have got these inputs like this, we have got this x, y and z as input and then when this 0 0 0 0 are added. So, sum is 0 and carry is 0, when 0 0 1, in that case sum is 1 and carry is 0. So, for 0 1 1, sum is 1, sum is 0 and carry is 1 and when it is 1 1 1, both sum and carry are 1. So, in this way we have got the truth table of the full adder. Now, it has got 3 inputs, the full adder has got 3 inputs, 2 are the operand bits, say x and y may be the operand bit and the third is the carry input C in. It has got 2 outputs sum and carry, and so for the Carnot map for sum is like this. So, if you draw the Carnot map, then it will be like this, that we have got this. So, this is basically the XOR. Okay. So, this is the XOR of x, y and z. So, this is basically this sum equal to x bar y bar z plus x bar y z plus x y bar z bar plus x y z, which is nothing but x XOR y XOR z. So, the sum is equal to XOR of x, y and z, and in case of half adder, you remember that the sum is equal to x XOR y. So, that means, if I use this half adder and we can make a full adder out of that. How? we will see that later. But this K map for Carnot map, K map for the carry output is like this. So, carry output is 1 whenever this y and z equal to 1, then or this x z equal to 1, x y equal to 1 or x y z equal to 1. So, if I draw the truth table and then make the grouping, so it will be like this. And so, I can say that is C equal to x y plus x z plus y z. So, it can be written as x y plus z into x plus y, and this x plus y can be written in this XOR form also, because if x and y both are equal to 1, then this term actually takes care of this thing. So, of this C output, but if this only one of them is equal to 1, then this z if z being equal to 1, so output should be equal to 1. So, I can change this x y term, x plus y term into this XOR form, and then it turns out to be x y plus z into x XOR y. So, z and x XOR y. So, in a half adder the carry output was x y, and in case of full adder, so we have got this as the carry output. So, if we consider the full adder function, so sum equal to x XOR y XOR z and carry equal to C equal to x y plus z into x XOR y. So, and the half adder function was s equal to x XOR y and C equal to x y. So, what we can do? We can use two half adders to get a full adder. So, here you see that in the first half adder we have given x and y as input. So, we have got x y as the carry output and x XOR y as the sum output. So, with that if we put this z as the second input, so second half adder has got this sum as one input and this z as another input. So, this x XOR y XOR z, so that gives me the sum s equal to x XOR y XOR z, and this carry is generated so this carry part. So, what we have done, we have taken a separate OR gate. So, this first this half adder, first half adder, so it gave x y as output in the carry, but what we need is x y plus z into x XOR y. So, this AND gate will be realizing that z into x XOR y, because x XOR y is coming here. So, it is in the half adder form. So, it is connected to the AND gate. So, it is connected here and then this z input is connected. So, here we get z into x XOR y. So, ultimately if I use an OR gate to OR between these two outputs, so you get C equal to x y plus z into x XOR y. So, that is the full adder logic diagram. So, using this half adders, so we can realize a full adder. Next we will be looking into another extension, like how can I have more number of bits in an adder. So, so far whatever we have seen a full adder, so it can have two inputs A and B and a carry input, and then it is producing the sum output and carry output. Just in the previous slide we have seen that a full adder, so it is having x y z as the two inputs, as the z may be considered as carry input, and it is producing a sum output and a carry output. Now, if you have got a number of if you have got to add a number of bits, okay, if the word size of individual numbers are more, say 4-bit numbers, then what we can do? We can connect these full adders in a cascaded fashion. Okay. So, this C0 is the carry in coming from the for the first adder. So, it may be if there is no carry for the addition. So, basically I am interested to do this addition, this A3, A2, A1, A0, this bit pattern I want to add with B3, B2, B1, B0. So, and there may be some previous carry coming into the thing. So, that is a C input, and if this carry is not there, then we can set it to 0, or this C0 can be set to be equal to 0 if there is no carry coming from the previous stage. So, carry coming from the input side. So, that way we can. So, what we are doing for the first full adder, so we are giving A0 and B0 and this C0. So, it produces the S0 bit and the carry 1. So, this A0 plus B0, so the C0, the sum comes here and the carry output goes here, The second full adder will add this C1, A1 and B1, it will produce S1 and it will produce another carry C2. Okay. So, C2, A2 and B2, so they will be added by the third full adder. So, this will giving S3 and C3 and this will be giving me S4 and C4. So, that is what is happening. Okay. So, we have got two 4-bit numbers, they are getting added and it is producing a 5-bit number consisting of 4 sum bits and 1 carry bit. So, this way in a straightforward fashion, so we can connect full adders and get the circuit for higher number of bits. So, C4 is the chain carry out to the carry in of full adder of bits A4 and B4. So, we can, if we have got the next stage A4 and B4, so we can chain it to the next stage. And C0 in this case is part of larger design. So, if it is coming from another such adder, then C0 may be the carry chain output of that adder. Otherwise, we can just set it to 0. So, we can now we can see the hierarchy. Okay. So, for 4-bit adder, so we can first design the half adder and use that half adder to design full adder and then use these full adders to get say 4-bit adder. So, that way we can have a clear cut hierarchy in the adder design. On the other hand, subtractor, so if you want to compute m minus n, and from our knowledge of this number theory, so we know that we have to add 2's complement of n to m. So, we should have this, so that is m plus 2 power n minus n. So, that is to be done. Now, if m is greater or equal n, so in that case we need only one adder and the complementer of n to do the subtraction. So, if m is greater or equal n, then we just we take the 2's complement of n and do the addition, that will give me the subtraction. However, if m is less than n, okay, so then we need to take 2's complement of adder's output to produce the magnitude of the result. So, if m is less than n, then after doing the, so the addition part is same or the same as the 2's complement addition part, subtraction part. So, m plus 2 power n minus n. So, that is done in both the cases, but for getting the 2's complemented result, so we have to do this 2 power n minus this, that is, that will give us n minus m. Okay. So, this is the adder subtractor design a plus b or a minus b. So, either of them can be done. So, this so here this S is the it is the S is a control. So, this S is low for addition and high for subtraction. So, if S is low, so here I am getting a 0, C0 is 0. So, it will be simply doing, so and these XOR gates, so they will be having this S input as 0. So, as a result they will be passing it as 0, the B0 will be passed here, B1 will be passed here, B2 will be passed here and B3 will be passed here. So, this will do the simple addition. Now, if you are doing subtraction, in that case this S will be equal to 1. So, this B0, B1, B2, B3, so they will get complemented via this XOR gate. In XOR gate, if one of the input is tied high, we know that it acts as an inverter. So, at this point I will get B0 bar, here I will get B1 bar, B2 bar and B3 bar. So, I will get the complemented versions there. And then this C0 is equal to 1. So, this is the I am getting A plus complemented 2's complement of B plus 1. So, that way I guess 1's complement of B plus 1. So, that gives us the 2's complement of B and ultimately that results in A minus B. So, this adder subtractor design is very simple. So, on top of this basic adder circuit, so we have got a complementer circuit which is consisting of a few XOR gates and that gives us the solution. Output is the result if A is greater or equal B. So, we just discard the carry bit and output is 2's complement of result if B is greater than A. So, if you want to get back the original value, then you have to take another 2's complement at this point. Now, overflow may occur. So, what is an overflow? So, when the result cannot be represented within the number of bits used. Okay. So, we are doing some 2 additions and then I am doing 2 4-bit number addition and the result can go to 5 bits. So, that way if I am using only 4 bits for their realization, so there is an overflow. Particularly for 2's complement number system, when I am doing this subtraction, so it can occur quite often. So, there can be two cases of overflow for addition of signed numbers. Two large positive numbers overflow into sign bit. So, not enough bits for the result, or two large negative numbers are being added and same, that is not enough bits for the result. So, as I said that 4 bit numbers being added, it gives 5 bit result, and the 5th bit is actually for the sign. So, if I say that way, then that will be affecting the sign bit. So, 7 plus 7. So, this is giving me 14. So, if I am so in 4 bit, so if I am representing both positive and negative numbers, we know the range is -8 to +7. So, the +14 cannot be realized, cannot be represented in 4 bits. So, that will give us an overflow. So, it generates no carry and C4 remains equal to 0. On the other hand, say if I consider -7 that is the result is -14. So, here also it is an overflow because I cannot represent -14 in 4 bits, but in this case it generates a carry. So, C4 equal to 1. If you look into that final carry generated, so this C4 will be equal to 1. Now, 4 plus 4. So, here the result is 8. Here also I cannot represent 8 is in 4 bits because the range is -8 to +7. However, it does not generate a carry, C4 equal to 0, and this 7 minus 7 there is no overflow, and but it generates a carry, C4 equal to 1. So, if you trace through the addition process, then you can understand. So, this overflow detection is basically if there is an additions adder subtractor. So, you have to compare between the carries generated at nth stage and n minus 1th stage. So, if these two carry, if you take an XOR of these two, then that will be giving us the overflow bit. So, whether it is overflow or not. So, the condition for overflow is either C n minus 1 or C n is high, but not both. So, that way this is the overflow condition. So, all the 4-5 cases that we have seen previously, if you make a summary of them, then you will see that it comes to some such conclusion, that is C n minus 1 or C n should be high, but not both. So, that is the condition for overflow. So, this 7 plus 7 only C3 is high. So, C4 is not high. So, that is an overflow. -7 minus 7, so C4 is high, but C3 is not high. So, that is also an overflow. +4 plus 4, so that is C n minus 1 is high, that is C3 is high. So, again there is overflow, and 7 minus 7. So, both the carries are generated, but there is no overflow. So, that way, so this overflow detection circuit is the XOR of C n and C n minus 1. Now, one difficulty with this type of adder that we have seen is that I have cascaded a number of full adders. Now, the second stage of the adder, it cannot work till the first stage has completed the addition and the carry bit is available from the first stage. So, that way if we go ahead, then for further and further stages there will be problem in terms of this carry not yet appear, not yet come to the adder stage. Okay. So, that makes this addition process or this ripple carry addition process pretty slow. Okay. So, another type of adder which is quite fast is known as carry look ahead adder, that we will see in this. So, this carry propagation is a problem. So, detect the end of propagation rather than wait for the worst case time to occur, and speed up the propagation via look ahead, carry select, etc. And it will limit the carry propagation to a small number of bits and eliminate carry propagation through the redundant number representation. So, these are some options. So, we will see them slowly. Okay. Now, you see that for a particular stage, okay, so if I take an example, then suppose this is a particular adder stage. Okay, so, it has got this xi and yi as the bits to be added, and Ci is the carry. Ci is the carry, and it produces the sum output and the carry output. Now, we try to see when a carry will be generated from this stage. So, the carry will be generated only when this xi and yi both are equal to 1. So, that is so irrespective of whatever be the carry coming from the previous stage, if xi and yi both are equal to 1. So, this is xi and yi, if both are equal to 1, then irrespective of whatever be the carry coming from the previous stage. So, it will generate a carry, this carry will be generated. So, if I have got a previous stage, so then this carry will be coming to this stage. So, this carry will be generated from this stage. And other condition is, other possibility of generating a carry at getting a carry at this point is, there was a carry coming to the previous stage and that propagated through this stage. And when this will propagate? So, this will propagate when only one of this xi and yi value is equal to 1, because in that case that 1 will be added. So, suppose xi equal to 1 and this carry I equal to 1. So, as a result this sum will be 0 and this carry will be generated at this phase. So, I can say that whatever carry was coming as input to this stage, that is getting propagated to the next stage. However, if both of them are equal to 1. So, xi and yi both are equal to 1. So, the sum is like this. So, anyway so this will be the output, and anyway this xi and yi being equal to 1. So, carry is already generated. So, here the generation and propagation does not have any separate meaning. So, they are all the same. So, we can say in summary that this xi and yi, so they are they will generate a carry if both the bits are equal to 1. So, xi the gi generate is equal to xi yi and propagate is equal to xi XOR yi. So, if only one of them is equal to 1, then it will propagate. Now, when a carry will not propagate, so it will not propagate or it will absorb if ai is xi bar and yi bar. So, if both xi and yi are 0, okay, then the carry that was coming from previous stage will get absorbed there. So, what I say is if this xi and yi both are 0. So, if there is a carry coming from the previous stage, then this will be getting absorbed in its sum and the carry generated is 0 from this stage. So, that is the absorbed signal. So, we can say that there is an absorbed signal ai, which is xi nor of so xi bar and yi bar, or the nor of xi and yi, and there is a transfer signal which is gi or pi. So, it will be transferred if it is if the carry is generated or carry is propagated. So, so this gi plus pi, so it can be written as ai bar, which is xi or yi, and C out is 1 given C in equal to 1, and the carry recurrence is like this. So, I can say that C I plus 1 is either the carry is generated at this stage or there was a carry coming from the previous stage and this stage allowed propagation. Okay. So, this was the expression is gi plus C I pi, and this expression can be simplified to be written as gi plus C I T I. Okay. Instead of C I P I, so I can write it as C I T I also, the transfer signal. So, this way I can say the how the carry recurrence occurs. So, I have got this C I is g I plus C I minus 1 into P I minus 1. So, if you just expand it, so you will get this C I minus 1 is g I minus 2 plus C I minus 2 P I minus 2 into P I minus 1. So, it is like this. So, if you go on expanding like this, so ultimately it will be coming to an expression in this form. So, you can get the series sum like this. Okay. So, it is g I minus 1. So, C I is equal to g I minus 1, that is the I minus 1th stage has generated a carry, or this stage k from 0 to I minus 2. So, kth stage generated the carry and the remaining stages they propagated the carry. Okay. So, this is the situation. So, this is so what we say is that so we have got these stages, So, whenever we are talking about, so this is the ith stage. So, either so at this point I have got this C I. So, either this so this is the stage I minus 1. So, from I minus 1th stage I have got the carry C I. So, C I is either at I minus 1th stage it was generated. So, that is given by this g I minus 1, or in I minus 2 stage the carry was generated and this stage just propagated it. So, this is g. So, k equal to I minus 2. So, it is generated here and it is propagated it is generated at I minus 2 stage and propagated at I minus 1 stage. or it is generated at any stage in this side. Okay. So, it generated at any k stage. So, some stage k at which the carry was generated, and then it got propagated through all these remaining stages. So, that is taken care of by this expression. So, this is telling that it is generated at stage k, and the stages k minus or k plus 1 to I minus 1, they are just propagating the carry. So, that way we have got this carry propagated, and then other possibility is that initially C 0 was there. So, it was given the carry was the input carry was 1, and then all the stages 0 to I minus 1, they propagated that carry. So, these are the three alternatives that we can have for the carry generation. Now, so if we are just looking into a 4 bit carry look ahead adder, so this C 4 will be equal to something like this. If we expand that expression, then C 3, C 2, C 1, C 0 like this. Now, S 0, the sum 0 is given by x 0 XOR y 0 XOR C 0, which is nothing but P 0 XOR C 0. Similarly, S 2 is P 2 XOR C 2, S 1 is P 1 XOR C 1. So, this way the sum and carries of individual stages can be written. Now, we can just optimize it a bit, having requiring 3 less gates, where the C 3 expression this C 4 is G 3 plus C 3 P 3, then C 3 is G 2 plus G 1 P 2 like this. So, we can just modify this previously written expression, okay, optimize it a bit, so that it will take 3 gates less. So, the circuit that we get is something like this. This C 0 goes to all the stages, then this G 0. So, this is actually this carry network. So, where this C 1, C 2, C 3 and C 4 they are generated. Okay. So, they are based on this generate and propagate logic. So, this is coming from this these expressions. Okay. So, this is straightaway implementation of these expressions. Now, so for carry look ahead generation, so we have got this expression in terms of I. So, I plus C, I plus 3, I plus 2, I plus 1. So, we have got these expressions. So, in general, so I will have this I will have this type of situation. Now, the difficulty is that you see the number of gates, it is increasing significantly. Okay. So, so it is so somehow at some point of time I do not want to generate further carries. Okay. So, I want to do some ripple carry, and that way I will make it simple, so that so much of gate is not gates are not required in the carry generation process.